Hello teachers, and welcome to our first chapter in Math 232, where we spent a lot of time talking about geometry. In this first section, 11-1, we're going to talk about basic notations, basically a lot of vocabulary. So when we finish this section, you'll be able to understand and explain basic undefined and defined terms of geometry, basic geometrical shapes, and learn the notation associated with each shape, attributes and properties of basic geometrical shapes and the relationships among them, and names, classifications, and measurement of angles. So here we have some terms. Notice point A and point B. Those are just points. Now what they have pointed to them is a compass, but what we're really defining here is point A and point B. You have line L. A good way to discuss a line is like the center line of a road. So they give you good examples here for discussion in the classroom. But a line, okay, is the center line of a road. There's line L right in the middle. On the edge, those are each lines as well, but the one identified is the one in the middle. And then you have a plane. So think about a plane as, say, a piece of paper, or they have a tabletop here to represent the plane. This is plane alpha. Notice they're using Greek letters here. Yeah, point C, I love this. They put a safety pin here to point out the point C. Again, a point doesn't take up any space at all. It's just a single dot, just a point. Here you have line M. Notice the notation. They call it line M. You could also call it line AB without any indication on the top of what it is, or you could put a line, notice the arrows on each end, which indicates that this goes on forever in both directions. There's line AB, or you can name it line BA. It really doesn't matter with a line which letter you put first, because the line extends forever in both directions. And notice we have a plane here, okay, plane ABC or plane gamma. Notice you can name a plane with 3 points, okay, or you could just name it what you're calling it, which is gamma. So a bit about lines. A line has no thickness whatsoever, and it extends forever in 2 directions. So just picture, again, an infinite line in both directions. Given 2 points, there is one and only one line that connects these points. So you're not picturing a curve, okay? So if I give you just 2 random points, let's call this A and B, there is a single straight line that connects those 2 points. So when you think line, think straight line. That's what we're really talking about. So there's a unique line that connects those and not more than one. If P and Q are any 2 points, we can create a number line on the line PQ so that there is a 1-to-1 correspondence between the points on the line and the real numbers. So you could turn this into a number line. Again, the idea is it's infinite. It goes in each direction forever and ever. So you can create a 1-to-1 correspondence with any line and a number line. Here let's discuss collinear. What does it mean for points to be collinear? Well, it means all the points are contained on the same line. So you'll notice here that point A, B, and C are collinear, but D is not collinear, okay, with line L. So line L contains points A, B, and C, like we just said. Points A, B, and C belong to line L. That's another way of saying it. Points A, B, and C are collinear. That means they all lie on the same line. Points A, B, and D are not collinear because they all 3 don't lie on the same line. So collinear just means they all lie on the same line. When you say a point is between another point, that means it fits in between. Point B is between points A and C on line L. Point D is not between points A and C. So when you're discussing between, you are still discussing collinear points. So even though it looks like D is between A and C, it's not. It's not the collinear, therefore you can't discuss D being between A and C. only B is between A and C. A line segment, you could also call this a closed segment, is a subset of a line that contains 2 points of the line and all the points between those 2 points. So a line segment is just a part of a line. Notice it does not extend forever to the right or forever to the left. It's just all the points, including the endpoints. And this is why they call it a closed segment, because closed means the endpoints are included, whereas open, and we'll talk about something that's open shortly, does not include the endpoints. And speaking of open, here we are. So you could have half open or half closed line segments. So subsets of lines that are sometimes identified include a half open or half closed segment, a segment without one endpoint, and an open segment, a segment without its endpoint. So look at the first segment that's listed above. That is considered half open because the point A is not part of the line segment. The point B is. So when you see a circle not filled in, that means that point is not included. On the other hand, B over here with the circle filled in black, that point is included on this line segment. Whereas the second line segment pictured, A, that point is not included and neither is B, so we call that an open line segment. So most line segments, just when you're speaking of a line segment, you assume they're closed unless you see or are told it's half open, half closed, or an open segment. Array. Array is a subset of the line AB that contains the endpoint A, the point B, and all points between A and B. So notice if you look at the first line that we have here, which is not truly a line, that's a ray. You see how it extends forever but only in one direction? And so you would note that as ray AB. So notice this, the notation. Notice the order you write that in actually does matter. It would not be ray BA. So when you use notation for a ray, you start with the endpoint and then you write the other point that extends forever. Okay, so a subset of the line AB that contains the endpoint A, the point B, all points between A and B, and all the points C on the line such that B is between A and C. Two rays are opposite rays if they have the same endpoint. That's important. They have to have the same endpoint. They lie on the same line, and their union is the line. So what we have here, this second, it's a line. It's really two rays. Again, notice how these rays are named. So this ray is named ray BC, and the arrow goes that way. The ray to the left is named ray BA. Okay, so you always start with the endpoint and then extend it to the direction that goes on forever. Now, a half line is a ray without an endpoint. So it's like an open ray if you want to think about it that way. But it's a half line, again, is a ray without an endpoint. A point separates a line into three parts, two half lines, and the point itself. So if you were to take the union of two half lines, you would still be missing the point B. So you would have to have the half line BA, union with the half line BC, union with the point B. So again, this is really important, that splits into three parts, each half line and the point itself. Okay, next let's define coplanar. Now, coplanar means they all lie within the same plane. And again, what are you thinking about a plane? Maybe a piece of paper, a tabletop. It's just a two-dimensional space. So let's go through each of these and make sure we're clear on this. Points D, E, and G are coplanar. Let's find them. So here's point D, E, and G. They all lie within the same plane. You see, they're all on that same piece of paper or tabletop. Okay? Now let me erase. Next, points D, E, F, and G are not coplanar. So we have D, E, and G, they were coplanar, but look, F is not contained on that piece of paper. It's out in space. So F makes that not coplanar. Okay, D, E, and G were fine, but not F. F is not coplanar with D, E, and G. Okay, next statement. And I'm going to erase and keep putting that back there. Okay, lines DE, DF, and FE are coplanar. So lines can be coplanar as well. So look at line DE. Notice that would be on that tabletop or that piece of paper. DF, okay, right here. Actually, not the same plane, DF, and FE. Look at that. So that's like a different piece of paper. Do you see that you could put a plane right here with lines DE, DF, and FE? Okay, now GE is not coplanar with that one. And we're not looking at the plane that's depicted in brown here. This is a different plane. Do you see how they all lie in the same plane? You got to get your three-dimensional eyes going. Okay, now next, lines DE and EG are also coplanar. So let's take a look at those. Okay, so lines DE and EG. Now they are on that brown plane that's depicted. Okay, I agree with that. Definitely coplanar. And then the last statement, let's see what they're trying to imply here. Lines DE and EG are intersecting lines. Okay, so DE and EG, they are definitely intersecting. You see they intersect at the point E. Oh, and that says that. They intersect at point E. That's exactly what I was trying to imply. So DE and EG are coplanar and they intersect at point E. So coplanar means they lie within the same plane. All right, skew lines. So lines GF and DE are skew lines. Let's take a look at this. So GF, I'm going to highlight in blue. I'm going to try anyway. That is not GF. Hang tight. There we go. There's GF. Okay, so GF and DE. Now, it almost looks like they intersect each other, right? But again, you've got to get your three-dimensional eyes working. GF and DE do not intersect each other. And there is no plane that contains them, okay? They are in different planes. They are not coplanar, which means they are skew lines. Okay, so if you envision, and do the best you can here too, lines that do not intersect each other, and they are in different planes. Okay, so they're just out in space, and they're not going to cross each other. On the other hand, concurrent lines intersect. Okay, so skew lines and concurrent lines are like opposite ideas. So concurrent lines intersect. Let's look at this. So we've got DE. So here's DE. Okay, EG. Notice they intersect at point E. Okay, they are also in the same plane. They're coplanar. But then when we add this EF to the story, those are concurrent. So they all intersect at point E, even though EF is not even in the same plane as DE and EG. Although EF is in the same plane as DE if you leave EG out. Okay, so again, I hope you're seeing this. And parallel lines, I know you're probably comfortable with parallel lines. They have no points in common. A lot of people say parallel lines never intersect, and that is true, right? They are the same distance apart forever and ever. Okay, but the main thing is they have no points in common. They do not intersect. Now let's talk about axioms about points, lines, and planes. And you may be curious what the idea of a notion and an axiom is. It's something that's accepted. It's not provable. So it's just something we have to accept to be able to talk about an area. And in this case, to be able to talk about geometry, we have to have certain ideas that we accept so we can prove other ideas based on these ideas. So that's what axioms and notions really are. And here's axioms about points, lines, and planes. Notice we've got 4 listed here. There's exactly one line that contains any 2 distinct points. So if you just randomly pick 2 points, point here and here, there's going to be exactly one line that you can draw. Now, you can't draw it curvy or anything like that, right? It has to be a straight line when you're talking about a line. So there's exactly one line that contains any two distinct points. If 2 points lie in a plane, then the line containing the points lies in the plane. Okay, so if I were to pick 2 points in a plane, the line would also be in the plane. I think that makes sense without me subjecting you to me drawing a plane. If 2 distinct planes intersect, okay, picture that. Okay, picture 2 pieces of paper intersecting each other, or 2 tabletops intersecting each other. Then their intersection is a line, right? Okay, and you're going to see that in just a minute, so I don't have to draw it for you. There's exactly one plane that contains any 3 distinct non-collinear points. Okay, so remember, what does it mean to be non-collinear? They don't lie on the same line. So if I just pick 3 random points, not collinear, like any 2 points can be collinear, but when you add a third one in there, okay, then that makes it non-collinear. But that will always define a plane. No matter what, 3 points will define a plane. Now, if you throw a 4th one in there, it might not be on that same plane, but 3 points will always define a plane. Now, also, to add to our list of axioms, a line and a point not on the line determine a plane as well. Now, that goes back to you need 3 points to define a plane. Well, if you have a line, if you have a line and a point not on the line, it's going to do the same thing. It's like having 3 points, because you could have 1, 2, and then there you go is your third. 2 parallel lines also determine a plane. So as you can imagine, if I just have 2 parallel lines, picture them in space, okay? You can always use that to define a plane. 2 intersecting lines also determine a plane. So if I know these are not skewed, they really do intersect each other. So it's not like one of them is way above the other one. They really do cross at this point or intersect at this point. That's also going to define or determine a plane. All right, so we have 2 pictures here. Here, alpha, the plane alpha is parallel to beta. So planes can be parallel to each other as well. And look, this is that intersection I told you I wouldn't draw for you because it was coming up. So again, picture plane alpha intersected with plane beta. See how it makes this line? So an intersection of 2 planes creates a line. There you go. You could also have a half plane, which is interesting. A half plane is a subset of a plane that consists of all points in the plane on one side of a line. Okay, so you can have a half plane, all the points on one side of a line. Now let's discuss angles. Okay, what is an angle? An angle formed by 2 rays with the same endpoint. So that's what an angle is. So notice we have ray BC at the bottom and ray BA angled upward there. Okay, now BA is called a side, ray BC is called a side. The point where they intersect, that's called the vertex. And notice the naming. You could call this angle B, okay, just using the vertex. You could also call it angle ABC, or you notice there's a 1 right here. We could call this angle 1. So angles are named many different ways. Sides of an angle is the 2 rays that form the angle. We pointed that out already. And the vertex is the common endpoint of the 2 rays that forms the angle. Adjacent angles are 2 angles with a common vertex and a common side, but without overlapping interiors. Okay, so notice the notation again. Angle QPR, so if I highlight this, this is angle QPR. It's also called angle alpha, you'll see. And it shares a side with angle RPS, also called angle beta. And those are called adjacent angles. So notice they share the same vertex. The vertex is P, but you're discussing 2 different angles, again, that are adjacent. Well, how about angle measurement? A degree is defined as 1 over 360 of a rotation about a point. So a lot of people think about a circle as 360 degrees, and that's exactly what they're saying here. So if we have a point, so here's my point, and we go rotation around the point, that's 360 degrees all the way around. And so if I divide that into 360 parts, one of those is 1 degree. Now a minute, we split that up. So we take 1 degree and we split it into 60 parts of a degree. So a minute is 1/60th of a degree. A second is 1/60th of a minute. Now I kind of like to write this a different way too. So you know that 60 seconds is equal to 1 minute. Okay. And then we know 60 minutes, just like time, is equal to 1 degree. So that brings me to the idea of how many seconds is in 1 degree. Well, if there's 60 seconds in a minute and 60 minutes in a degree, 60 times 60, there are 3,600 seconds in 1 degree. And you've seen it. The notation for degree is that little circle. We can use that. All right, finally, we have our first problem. It says, find the measure of angle BAC. So let's make sure we're clear on what BAC is. So we've got BAC. So that's what we're looking for, okay? Now, we know the measure of angle 1, which is really these adjacent angles put together. So notice it goes all the way from the bottom to the top of line AB, okay? Or ray AB, and it looks like more like an open segment there. And then angle 2 is here at the bottom. So how would we find the measure of angle BAC? Well, how about we subtract 2 from 1? So angle 1 is 47 degrees, 45, by the way, that's notation, degrees, minutes, and 2 lines would be seconds, so that's like 0 seconds. So you can see that notation. Minus, okay, angle 2. So that's 29 degrees and 58 minutes and 0 seconds. Again, the only reason I'm throwing those 0 seconds in there is so you could see the notation. That's it. And what are we doing? We're doing the measure of angle 1 minus the measure of angle 2. That's how we're calculating this. Now, how are we going to do this? You may want to even write this vertically. So if I were to write this vertically, I'm just going to write the 29, 58, 0 right under here. So minus 29 degrees, 58 minutes, 0 seconds. Okay, so clearly we have 0 seconds to the point where I'm not even going to include seconds in my answer. But I've got to subtract, y'all, 58 minutes from 45 minutes. How am I going to do that? We're going to regroup, right? Okay, so we're going to exchange one of these minutes here. So I'm going to remove one of these 47 minutes. I'm going to turn this into 46, degrees. I'm saying minutes. And I'm going to move over here an extra 60 minutes. Remember, 1 degree is 60 minutes. So now I have 105 minutes minus 58 minutes. And that's going to give us 47 minutes. And then 46 minus 29 gives us 17 degrees. So I do believe that angle 1 is 17 degrees 47 minutes. And I have it typed up for you, but it doesn't go into all of this detail, so that's why I wanted to show it to you by hand. But here's the typed up version. It just says the measure of angle BAC is 17 degrees 47 minutes, but no explanation of how to get there. And so that's what the previous example did. Now there's a question B to this. They want us to express 47 degrees, 45 minutes, and 36 seconds as a number of degrees. So they want this as degrees only as a decimal. How could we possibly do this? Okay, degrees only. So remember, we're going to leave the 47 degrees, right? Because it's already in degrees. So we have 47 degrees. Make sure my pen is working properly. And we're going to add that to, now how do we change 45 minutes to degrees? Well, remember, there are 60 minutes in 1 degree, so we know this is less than a degree. We're going to take that 45 minutes and divide it by 60 minutes, and that's going to change it to degrees for us. What about the seconds? Okay, so you've got 36 seconds divided by, how about 3,600 seconds? Again, why am I doing that? Because remember, we're changing seconds to degrees, and there are 3,600 seconds in every degree. Now, this is going to take me to a decimal. This is going to be 47, and then 45 divided by 60, and I'm just doing this in a calculator. You could do it by hand if you needed to, is 0.75. I don't need the 0 there, I just need the 0.75. And then 36 divided by 3,600 is 0.01. And that's going to give me 47.76 degrees. If I look at the typed up version, there it is right there. So again, to change minutes to degrees, we divide by 60. To change seconds to degrees, we divide by 3,600. Now, let's talk about types of angles. An acute angle, here we have AOB, measures less than 90 degrees. So acute angles are less than 90 degrees. Right angles, I know you know this, are exactly 90 degrees. Obtuse angle, notice here, AOB, is between 90 and 180 degrees, and then a straight angle is exactly 180 degrees. What I've added down here at the bottom is because when I worked on the homework, I ran into the idea of a reflex angle, and that wasn't defined, or maybe in a later problem, but a reflex angle is an angle that measures between 180 and 360. So it would go over the straight angle. So maybe if I drew a line here, okay, and shaded all that in, that would be a reflex angle. How about a circle? The set of all points in a plane that are the same distance, which is called the radius, from a given point. That makes sense, right? That is the definition of a circle. So you pick a fixed point, say here in this circle on the left, okay, from here to here is that set distance. And if you were to plot every one of those points that's the same distance from that point, that would create a circle. And this value right here is called the radius. Often we use R for the radius. All right, the next is an arc, any part of the circle that can be drawn without lifting a pencil. So here they've got noted, this is arc CD. Okay, notice the notation too. They put a little arc over it, or you can write the word arc CD. Okay, now there's more. We've got a chord. Notice this is a chord. Okay, it's not the diameter. So a chord is a straight line from one point to another point on the circle that doesn't go through the center. Whereas the diameter, if I highlight that one, it's like a chord, but it goes through the center, so it has a different name. Also, they point out over here, this is arc AB. And our definitions keep going. So chord is the one I just mentioned. Remember, any segment with endpoints on the circle. So again, a chord right over here, it does not go through the center, whereas a diameter goes through the center of the circle. And don't forget the radius. The radius is from the center out to any point on the circle, and it's half of the diameter. That makes sense. And it's also how the circle is defined. More definitions. So we have a minor arc. What is a minor arc? Is one determined by a central angle whose measure is less than 180 degrees. So an example in our picture down here of a minor arc is AB. Notice that angle is less than 180. Remember, 180 is halfway around, okay? While a major arc is determined by a reflex angle. Remember, I just defined that for you, whose measure is greater than 180 degrees. Let's go back here. It says a major arc, ACB. Okay, so how do we do this? Here's C, here's B, here's A, but that is less than 180, right? You got to do this in order. So this is A, and then we go C, B. So that blue is your major arc. So when an arc is named, you need to go in the right directions with your lettering so you can follow what arc that is. It says, depending on the context, a central angle and its associative arc have the same degree measure. So if we said that this angle over here, the angle AO, let's use a different color highlighter. Let's use pink. The angle AOB, let's just say that was a 30-degree angle. Then the arc I've got in green here, AB, would also be 30 degrees. That's what that's saying. Okay. An arc determined by diameter, remember a diameter goes through the center, is a semicircle. So if I change colors on you once again, let's go purple. So the diameter goes all the way across, and then this arc associated with the diameter is the semicircle AD, or arc AD. The semicircle of circle O in the figure also is considered to have center O. So when you talk about a semicircle, they have the same center as the circle would have. So I've reached my 30-minute mark, passed it just a little bit, but I'm not finished with this lecture. So let's come back for part 2, where we'll do lots of examples. Hope you have a wonderful day. Let me know if you have any questions.